so let's get started. So let's start by looking at the schedule of the class. There's some things coming up. Hopefully you all got the homework turned in already, assignment 2. The next homework will be posted later today on clustering. So you should be able to start looking at that right away. I have it due the Wednesday right before the midterm because there will be topics about clustering on the midterm. So I figured you'd want to do it before the midterm. But you should look for that online. I'll post the announcement on Canvas. It should be similar in scale to the first 2 homeworks. The other thing to look at is the data collection report is due on Monday. Hopefully all of you got feedback on your projects. We hadn't made the groups yet, so some of the comments only went to one person in the group. So talk to everyone else in your group. Most everyone had good projects and were on the right track. I wanted to talk a little bit about what goes into the data collection report, which is due next Monday. Since this is, it's always, I mean, it can be confusing what I'm asking for at this point. And so first understand the main mechanism of this, the goal of having you turn this in is so that you're still working towards the project, even if you haven't, say, witnessed all of the techniques you need in the class yet. So I want you to try and, so not just to download a data set, but start thinking about how you would represent this data set. So a lot of what we talk about in this class is you take some data, whether it's a document or something, and you convert it into some other format. And once it's in that format, then you can run an algorithm or do analysis on it. And there's some modeling involved here. And I want you to kind of start thinking about that process in this data collection report. So not just downloading and say, I've downloaded it onto my hard drive, but you need to you may need to clean the data a little bit, to filter out elements of it that you don't want. So certain aspects like that. So let's go through these points. Can people read these? Maybe make it a little bigger. So the 3 things that you need to, or the 5 things that are required. That's readable. So these are, I mean, these questions are not meant to be hard. If you kind of do something reasonable, you'll get all the points. The first thing again is I want you to do at most 1 page. A few of you turned in project proposals that were too long, and I need to put page limits, otherwise people just keep making them longer and longer and longer. So I'm doing this for your own good. So at most 1 page description for this, a little bit more than the project proposal. And don't feel the need to make the font smaller. I'm not going to enforce stuff like that, but you don't need to write that much. So talk about how you obtain the data and how large it is. And these are mainly because, based on what your proposal is about, you may need a certain quantity to see a certain phenomena that you're trying to find. And we can give guidance and say, this is not going to be enough data for what you want to do. Or maybe it's so much data that you're just going to spend all the time kind of wrangling the data and not be able to do something interesting. So I'll tell you, actually, you want to throw away most of that data just because it's going to get in the way of you kind of exploring what you want to do. And so it depends on on your scenario. So you can do something like what is the gigabytes, but something more useful is like the number of data points, or the number of attributes that data points have, or something else like that. That'll allow us to give more kind of specific and useful feedback. And then the third one is what format are you storing it? For some of you who have taken database class or 2, you may say, I'm going to load it into a certain database, and that's okay. What I really want you to talk about is kind of the abstract data type here, right? I want you to say, I'm going to represent this data as a matrix, as a point set, and the underlying distance may be the Euclidean distance or the Jaccard distance. And you can change these things. You can say, I'm not sure what distance to use. We're going to explore that sort of things. But I want you to think about the format of the data, not just is it in a database, but what abstract data type are you putting it into so that you can then process it with algorithms we'll talk about in class. And so part of this, so the fourth one is like, how did you process it to make it easier to use? So you should have done some processing on the data at this point. So I'm asking you, how did you do it, right? So just as a way of checking that you've actually done something. And you don't need to be too detailed here. I just want to know roughly how you did it. Did you throw away certain, like if you have Twitter data, there's lots of metadata you probably don't need. You can throw that out and so forth. Okay, so then the fifth one is always trips people up, is how would you simulate some data that's similar to the data that you're working with? So I think all of you had projects where you're planning to work with a specific type of data or a specific data set. I'm asking if you didn't have access to this data set, or let's say the data set was not going to be large enough to really see all the phenomena you wanted to find with the data mining algorithm, then how would you simulate data so it looked bigger, so you could see something about what happens when you scale the data? And so just saying, if you're representing your data as a matrix, just putting random elements in the matrix is probably, it might work okay, but you might want to put more structure in there. And so for matrices, we'll talk about SVD and PCA, and that may be helpful later. But, if you don't know how to answer this one yet, some of this we haven't covered in class. If you're dealing with graph data, this is still kind of a challenging way. You want to generate a large graph that looks like it's a social network, for instance. Well, people have studied large random graphs that you could generate in mathematics for a long time, but typically they assumed each edge was equally likely to exist in the graph. And social networks are very different than this. So you want to simulate it so there are different types of nodes and different sorts of communities in the graph. And so, you may not be able to completely answer this question, but try and think about it, what you would do. And then it's good to keep this in mind as you're doing it. It allows you to understand various aspects, kind of how what you're doing might interact with aspects of the data. Okay, is that clear? Any questions on data collection report? How this will work? Okay, so I'll do Monday. Shouldn't take too much effort to write up the report at this point, but you need to start collecting your data. A lot of you have already kind of downloaded data, so you just need to kind of look at some basic processing. All right. Good. Let's get into the lecture. So today we'll talk about, we're going to be talking about spectral clustering, which is the third general type of clustering that we'll be discussing in this class. And just like the hierarchical and the assignment-based were very different from each other, this one is probably going to be even more different than the other two, if it's right. So spectral clustering, instead of working on point sets where you have a distance, the input here is the input to this is going to be a graph. And so so how many of you, you've taken like 2100s or you've worked with graphs before? This is not a new concept. Anyone's not heard of a graph? Okay, so let's just draw an example. I'll use an example graph. Can you read? That's an A in there. And we'll use this. Okay. Okay, and so the elements of the graph are going to be the things that you want to cluster. So these are like the data points, but instead of having like a Euclidean structure, what you have are these edges in between these nodes. Okay, and so this is, your input will look something like this. It probably will, if you're doing this, probably it's not going to be so small actually. So one strange thing about this is a lot of examples you see often will look like these small graphs that you can draw on a piece of paper. And those will be a lot easier than if you're actually working with much larger graphs. Then you won't be able to use all the same intuition, but we'll develop a mathematical framework which will generalize, where you don't need to see what the pictures look like. Okay, so now to find a clustering of graphs, well, the spectral clustering is going to be top down. So what this means is that it's going to find a cut in the graph. So we're going to take this graph as going to be, often you write this G as V is a set of vertices and E is a set of edges here. And what you want to do is divide up these vertices into two sets, S and V set minus S. So everything in the set S, these are both going to be subsets of the vertices, subsets of all my vertices. So these are subsets of the vertices, and I'm dividing them into two groups. So as we'll see, a good clustering of this graph is going to probably look like these could be a subset. So then S would be the set A, B, C, D, right? And then everything in the everything else. So we'll write this as the V set minus S. Maybe we'll call this, say, S prime. Then S prime would be everything else, which is E, F, G, H. Okay, so you just need to divide the graph into two parts, and then if your goal is not to find two clusters but more, then you just apply the same algorithm so recursively on the subgraphs, right? So the subgraphs of S, right, is, so I can have a graph that's induced by S. So this is going to be the set S, and then all the edges that are in between two vertices in S, right? So the set S is as above, and the set of vertices is going to be, the set of edges is going to be something like, there's an edge AB. And so notice these are, I'm not going to talk about graphs that have a direction between the edges right now. So an edge is just going to be a pair which is unordered. So again, I use these squiggly brackets. So as AB, it has AC, it has AD, and it has BD and CD, right? So it's all the edges that are in between vertices in the subgraph. It does not include the edge CE. Okay, CE has one of the endpoints in the subgraph, the other one's not, so I don't need to look at this. So then once I have this once I have this subset of the vertices, then, sorry, that notation should be ES. It's probably very confusing. These are the edges. So that's why I was saying vertices instead of edges. So these are the edges defined by this subset. Okay, so once I have this subset of the vertices, then I can look at just those edges inside there, and then I can recursively apply a technique to try and find clusters within this set ABCD, the set S here. Okay, so this is the general framework. So what we need to be able to do is to find this good way of dividing the graph into two parts. After we do that, we can keep recursively doing this until we're happy, or we reach some number of clusters, or we reach some threshold in a similar way. Similar aspects we had with the hierarchical clustering, which was the bottom up instead. Okay, so then you do this. So then recurse on S, ES, and S prime, ES. Okay, great. So this is the general framework. So the key thing now is finding a good cut, a good way to split the vertices. Okay, so what would we want in a good cut? What makes the one I've drawn here good? What was good about that?
You only cut one edge.
So I only cut one edge. Good. So two properties that we're going to want. Of good cuts. So one is that will say that so we're going to say that the cut between S and S prime is going to be small, and this is exactly going to be so just the number of edges. So it's a number of edges where one vertex is in one side and the other vertex is in the other side. Right? So this is the only edge in the cut. So this is the only edge that's cut here. So we want this to be small. Okay. So good. So is this going to be enough? Yeah.
The cardinality of the vertices is about the same for both.
Yeah. Okay. Good. Right. So we also want something where the graph is balanced. The cut is balanced on either side. We want them to be about the same size. Otherwise, I could also do a cut here, and this one has the same number of edges which are cut. But you see, like just chopping off this H vertex seems much less useful than dividing by this on the CE edge, because I'm not going to do much of my recursion. I basically get most of the same graph I started with, and the other side just has one vertex, and it's very boring. And so in very large graphs, this would happen a lot. There would be a lot of these social networks and stuff, these dangling vertices that have very few edges, and you'll tend to just cut these off if you're just trying to minimize the cut. So you want some way to balance so the two sides of the cut. And so what's typically used is what's called the volume of one of these subsets. So the volume, now you want this to be big, and so this is going to be the number of the induced edges. Well, it'll be a little bit different than the induced edges. The number of edges, it's not just the number of vertices. The quantity we really care about is going to be the edges, it turns out. So the number of edges with at least one vertex in S. Right, so in the example we have up here, this cut for S, it's going to have these 5 edges I've talked about here, right? Between the ones inside of it, but also this edge CE. I'm going to count that one as well. So I'm going to count the edge CE. So in this case, the volume is going to be 6. And then what would the volume be for S prime, everything outside of this S?
5.
Yeah, that one's going to be 5, right? There are 4 internal ones, and then the CE edge goes across. Okay, so now, so we want that the cut is small and the volume is big. How would we, having two different individual kind of properties by themselves, it's kind of hard to work with. So we want to combine these together in some way. And a very popular way, and there are actually a few ways of doing this, is called the normalized cut. And so this is called the end cut of, say, S prime. This is going to be cut of S prime, volume of S. But this by itself isn't good, because then I can just make the volume big by having S. I can have the same cut, and or I can have the cut that goes to H here, but instead of having H in the set S, H would be S prime, right? So I could have the volume very big for S. So I needed the volume to be big both on S and S prime. So what you write is cut of S prime over the volume of S prime. Okay, so I need the volume to be big on both sides. Okay, so let's go and look at these examples up here. So we'll call this T, and then the other part T prime, and then we'll call this one S, this cut. So let's calculate the normalized cut score for both of these, of the subsets here. Right, so what is the normalized cut score for S and S prime? Remember, it's going to be
1 over 6 and 1 over 5.
Yeah, right, so the cut size is 1, so it's going to be for S and S prime, be 1 over 6 plus 1 over 5, and this turns out to be something like 0.367. And so let's do this instead for the normalized cut, for the end cut of T and T prime. And so this, again, the size of the cut is going to be 1. So I have 1 over here, 1 plus this. I haven't escaped that yet. Okay, so what is the size? The cut of T, so now it's symmetric whether I use T or T prime. The cut of T is going to be 1. The volume of T is going to be 1. There's only one edge that goes from H to G in the set T. And how many edges on the other side? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 1 and 10 now. And so this is, it's going to be 1 plus 10. And so this is going to be, what is this? Is 1.1. So for the cut T now, which just cut off the single vertex, this is not much larger. This was 1.1. This is 0.367. Right, so I've got a much smaller normalized cut score for the one that divides them equally. Right? And it turns out this normalized cut works pretty well. There are other variants, but I think from what we've from what I've read about this and seen is that the normalized cut is a pretty good one to use in practice. And so I'll talk about two ways to find good cuts, and one of them, and one will be optimized for the normalized cut, and one will be optimized for a different cost function. I forget, maybe that's, the other one may be something like the product of the volumes on the bottom, or something like that. And that one works okay, but I guess slightly less well. Other versions of this might be slightly mathematically nicer in some context for proving results in theory, but this one works fairly well in practice. This normalized cut is a good thing to try and minimize in your cut. Okay, so how would we find a good cut? Right, this seems like a hard problem. With the hierarchical clustering, we could kind of merge things from the bottom up. This seems kind of simple and straightforward. With the assignment base, we could pick centers, but now it's hard to think about these centers in a way that's useful. For instance, using like the distance to walk on the graph from one of these vertices, like in this picture, if I pick like B and F, right, those might work okay if I said the distance from either of these is the number of hops. But in much larger graphs, this doesn't work nearly as well. There's these things called like these, so like this, there's this thing called the small world phenomenon, where supposedly in these large social networks that the number of hops to any person or an average person is supposed to be small. Something on the order, like originally there was this experiment by, I think by Milton in the 1950s where he tried to connect people like in the mail. This is very pre-internet, right? And they had, so what they said is he gave a bunch of people a task of trying to get a letter to someone he gave someone else's random address. And he said, mail it to someone who you think knows someone who's going to be closer, right? So mail it to someone who you think knows someone who may know someone who can mail it there. So people would send it to someone who lived in that state, that they knew the address, or they knew someone who lived in the right city or something like that. And average, it turned out that of the ones that were successful, which I think was only about 20%, it took about, I think it always concluded in like at most, so 7 hops. It took only 7 sends of the letter. So there's this notion of the 7 degrees of separation. And so then, but people have been saying with the internet, this should become much smaller. And so Facebook recently released some study which seems kind of somewhat controversial, kind of partially just for the headlines, that said the average distance between any two people based on who's friends with who in the Facebook graph is like 3.5. So for any person in the Facebook graph, you can probably find a path that's 3 or 4 people in order to in order to kind of have friends of friends of friends of friends that's connected to these other people. Right, so these notions of kind of distance based on the graph hops, it's kind of may not work very well because a lot of people are going to be about the same distance. They're going to be ties. Like half the graph may be 3 hops away. Right, so if you say 2, well then that's very restrictive as well. So these are kind of, you can't use the same sort of intuition anymore on graphs. Things break down. Okay, so now that I've told you these things that don't work very well, what other ways could we possibly do? Like, what's another way to deal with graphs? So what we're going to do is we're going to switch our abstract types. And so this is going to be very cumbersome to draw, so I'm going to use slides again. And hopefully this, I can do this okay. So we're going to look at this graph again here. And the idea is we're going to represent it as a matrix. All right. Okay, so we have this graph, same graph, and here are all the edges and listed out. So you can draw it or you can write it out as a list of edges, or you can write it as this matrix. You can think of it as kind of like a chart or something where you have each node is a letter or an index into the row or the column, and there's a 1 if there's an edge, and a 0 if there's not an edge. Okay, so then you could write this as a matrix, like in MATLAB if you use MATLAB. We'll do some experiments with matrices later in the class, so the clustering homework you won't need to use the matrix part of it. So we're going to use this representation as a matrix. Now, before we talk about how to take advantage of this, what's kind of silly about this representation?
Matrix is like sparse.
Yeah, it's going to be super sparse, meaning that there are going to be a lot of these entries which are 0. So look, if I look here, right? So if I look at this row, this was with this node H, you can see that almost all of it is zeros except for this 1, 1, right? And for much larger graphs, this is going to be, you know, even more true. You're going to get very, very sparse things where something like less than 1% of the data is going to be non-zeros. It could be 1/100th of 1% in some data sets. Now, it depends on who you talk to. Some people will say, well, as these graphs grow, various ways you can get these sparse matrices, or these graphs that what is the rate at which the number of, the average number of edges grows per column. And so some say, well, it's going to be something close to constant. That used to be the prevailing thought, or maybe it was something like it was log n. If there are n people, then you're going to have about log n edges on average. But there are also studies that say it's like a polynomial. So the number of edges is going to be roughly v to the 1 plus c for some constant. Right? So in this case, the maximum number would be c would be 1. That means that it's completely connected. But you get numbers where c is going to be something like 0.2 or up to 0.5, depending. So it could grow polynomially large. But if you look at like polynomials, like taking something to the power 1.2, it's still much smaller than the whole graph. If it's very big, that could still be less than 1% of the entries are going to be ones. So even though you're used to thinking in like an algorithms class that log n is so much smaller than a polynomial, well, for these scales, the polynomial is still very, very small. Okay, so we're going to use this graph, this matrix representation, and there'll be ways we can deal with this sparsity implicitly. That, like in MATLAB, there's a way you can store this in a sparse format, and then it basically has this vertex edge representation that it stores internally, but you can do operations on matrices you'd normally want to do, and it's optimized to only kind of look at the entries which are non-zero. So there are quite a few mechanisms to deal with the sparsity, and we're going to kind of ignore those for this lecture. But if you really want to scale this up, then that's what you want to do. Okay, so what we're going to want to do is not just look at oh boy. Okay, so we're not going to want to look at just this matrix here, where this is just what's called the adjacency matrix. So I'll write this as A. This is the same matrix we had before, the same representation, this adjacency matrix. For every row, this corresponds to G, row G, and say column E, right? Then there's a 1 here, right? We also want to look at what's called the diagonal matrix. And so this one only has entries on the diagonal going down the middle here, right? So it only has entries here. So this is forcing it, of course it has to be very sparse. So if there are n data points, there are most n entries in it. And this diagonal or this often called the degree matrix, it says for each entry, this is A and A, right? So I could have a self-edge maybe in the adjacency matrix. You could say something like there's a self-loop. But in general, what's counting is the degree of every vertex. So it's how many edges does that vertex have. So A has edges with B, C, and D, so its value is 3. B has edges with just A and D, so the value is 2, and so on. Okay, so again, very simple. You can represent as a matrix, but you can think of it much you could probably want to internally represent it in a different format. And so then what we want to construct is some matrix called the Laplacian matrix. Okay, and there are a couple of versions. This is the unnormalized. We'll talk about the normalized as well in a little bit. The Laplacian matrix is just D minus A. Right, so it's basically I filled in the diagonal of this with every with all the entries of the diagonal matrix of the degree matrix, And then I filled in the adjacency matrix by just subtracting, by just putting a negative sign on each of these. Okay, so this is the Laplacian matrix. So it's a little, I personally don't have a great intuition of what this is. Well, okay, yeah, so actually there is some cool intuition of what this is meaning here. One way you could think about this is that you can think of the D matrix as the amount of flow, like you can think of there's water flowing around this system, and there's D is the amount of flow, water flowing into the vertex. Right? It has so many other vertices, and so each of them is sending some water or something into it. And then the A matrix is saying, where's that water going? There's some sort of equilibrium here. We'll talk more about various sorts of these equilibriums with Markov chains later in class. But in this case, you see that the sum of every one of these columns is going to be exactly 0. Right? The degree is going to be exactly the number of minus ones in there. And you could model this differently. You could say instead that there are 2 edges from A to B, and then you'd have a minus 2. You could do that. And then the degree would also increase by 1. You can model things slightly differently as well. Okay? So now we have this matrix. And now if you kind of look at this, squint at it a little bit before we actually say how this is going to work. Because I've represented the vertices in alphabetical order, it turned out to be the right order, you're going to kind of see these big blocks of zeros, or mainly zeros here. Right? This one goes up here, right? So I want to say, look, there's not much stuff being connected in here and in there, so I kind of want to break it kind of across this way. This kind of makes sense. And so the ordering of the vertices didn't really matter, so let's say I can reorder them in some way. So I somehow want to find a way to order the vertices. In this case, maybe alphabetical is a good way to do it, but ahead of time, that's not something we know. Somehow reorder the vertices so I can cut them somehow. So on one side is one set and one side is the other set. Okay? So this is kind of the intuition. Again, this seems like a hard combinatorial problem. I have to keep checking all these reorderings and so forth. But it turns out this matrix representation is going to be very useful because we can calculate what's called the eigenvalues and the eigenvectors of this matrix. Right? So who's worked with eigenvalues and eigenvectors before? And for who is this an unfamiliar concept? Okay, so we'll briefly mention this. You should have taken these in a linear algebra class. If you have a matrix M, then an eigenvector of this matrix is a V such that, so there exists a scalar. So this is a matrix and this is a scalar. So if I multiply the matrix by this vector, I'm essentially getting the vector back up to some scale. Which should seem, so this matrix needs to be a squared matrix, right? And so in order for this to work, so I get back the same vector. This means and so the eigen is a German term meaning something like self. I'm not sure if I've heard different translations. But it's like you're getting back the vector when you multiply it by the matrix. So this is what the eigenvector is. And it turns out that the number of distinct, these are very special vectors, and the number of distinct ones is up to the rank of the matrix. Is the same as the rank. And so I've listed them here. And so this value lambda is the eigenvalue. And so for this unnormalized Laplacian, and this is of the graph here, I've written out all the eigenvectors as columns. So this is the second eigenvector, and we'll call this V2. And this is the second eigenvalue, and we'll call this lambda 2. Okay, so the first one is going to be, for the unnormalized Laplacian, the first one is going to be really boring. It's always going to be 1 over square root n for each entry, and the eigenvalue is going to be 0. And this one we just ignore. And so if you want to actually calculate this, for the purpose of this class, it's just going to give us, you can just, you can call in MATLAB. So for a matrix L, you call this Eig function, EIG, and returns, you can return a matrix V where the columns are shown here, and the eigenvalues in L, which is going to be this, if it's a vector or if it's just a, I think that's going to be a diagonal matrix with the eigenvalues on the diagonal. So you can just call this at MATLAB. This is a very well optimized thing. So we just need to call this and we get back this matrix. Okay, we're going to get back this data, these eigenvectors and these eigenvalues. Okay, and so now it's going to turn out that it should give them to you in sorted order. So the smaller eigenvalues come first. Right, so the 0 one you ignore. The second one is going to be interesting. The second one is called the Feeler vector of a graph. And so this is a really kind of it comes up in many contexts where you want to do this. Okay, so this Feeler vector, if you look at this has encoded in it everything we're going to need to know to do this split, it turns out. If you look at the numbers in here, how do they correspond to how we split the data into S and S prime? And what we decided was the best cut. Yeah, so the ones which are negative are in S, and the ones which are positive are in S prime. Right? And so actually, the sign of all these, if you multiply them by a -1, it doesn't really change much information. So the fact that one's negative and the other's positive doesn't mean much, but the negative ones are on one side of the cut and the positive ones are on the other. In fact, it's kind of more interesting than that. If I just look at, so I'm just looking at V2 and V3 here, so the first two eigenvectors. What's going to happen is that if I just look at V2 and I use those as the x-coordinate, and if I look at V3 and I use those as the y-coordinate, but just look at V2, just look at the x-coordinate, then they were minus signs, minus 0.42 for B, minus 0.36 for A and D, minus 0.2 for C, right? And then plus 0.17 and so forth for E, G, F, and H. That tells me like how to draw them on a line, right? This first eigenvector says, what is basically the best way to draw these vertices on a single line? So then if I want to find a cut, I just can look at them in this ordering. And so often, you can just say, I'm going to split on 0. Right? Let me color here. So I want to split here on, it might be useful to split here on 0. In some cases, what's going to happen is there's going to be a big gap, and it's going to be not exactly at 0. You may get something where you draw them, and you get, so this is the 0 point. You get a bunch of things that look like this, and then you get other ones out here. And so then you want to split here, where this was 0. So what you want to do is take this one dimension, and then draw them in this one dimension, and then look for good splits here, where there's a big gap between the values. And if you're too lazy to do that, you can just split on 0. Okay, that's usually a good first thing, but sometimes you want to actually split on something other than 0. Okay, and then if I look at this, the third eigenvector too, then I can draw based on that, and then I get a two-dimensional picture. Right? I'm going to get this two-dimensional picture, and so this allows me to do more after that. Right? So let's say instead of rerunning this eigenvector decomposition, because it takes a lot longer than reading just the data to compute it. So maybe I want to reuse some of that. So I can do something like, well, I'm going to look at it And the ones in each of the quadrants, so these are in the same quadrant, these are going to break into 4 clusters this way. I can look at the splits based on the first 2 eigenvectors, based on the positive and minus, the positive and negative, or I can look for other ways to do it. So if I was forced to go into 4 clusters, this seems like a pretty reasonable thing to do. One, I wanted H off by itself, and if I had to split this side, C is kind of connected to E in some way, so it's much less kind of tied to that other part of the subgraph S. Okay, so let's keep looking at this. There's some other cool properties involved here. So what happened with A and D here? Let's look at these guys. A and D are right on top of each other. What's going on? Is this just kind of a weird phenomena that happened on this data set? Or is there kind of, why would they go right on top of each other?
Is it because they share all their neighbors except they're neighbors with each other?
Yeah, so they have the same set of neighbors except for each other, right? So if you look from a graph perspective, they basically look exactly the same, right? There's no difference between A and D from the perspective of the graph. So these eigenvectors have not really been able to distinguish them, but that makes sense. All the information about the graph doesn't say anything different about them. So why should it give them values which are different? If I look back at all of these eigenvalues, so there's A and D, so the first and the 4th row here, they eventually become different here in the last one. And this is kind of essentially arbitrary. One got negative 1 over square root 2, and the other got positive 1 over square root 2. Okay. So these really didn't get separated. What else happened in this drawing here? So one way I drew this, this is not the only way to draw it here. You might also instead do the coordinate of these. So these coordinates did not use the eigenvalue at all. It just used the eigenvector. But these eigenvalue kind of should tell me how important each of these eigenvectors are. The smaller the better. Right? It's the intuition I want to say. So a better way of doing this might be to have the coordinate of A. So I want to do an embedding of A into R2. A better way of doing this may be, so this is V1 of A times 1 over, or this is V2, lambda 2, as the x coordinate, and V3 of A as 1 over lambda 3 as the y coordinate. So basically, if the eigenvalue is really small, I want the coordinate to be bigger, and this will stretch out the graph more. I don't think I have a picture of this. Okay. So I don't think I have a picture of this one, but if you're going to draw them, this tells you a better way of drawing them. It says that what would happen is the x-axis would be much more spread out than the y-axis. Because the first eigenvector tells you much, or the second eigenvector tells you much more than the third one. And this is roughly the right way to do it, by multiplying the coordinates by 1 over the eigenvalue. Okay, so, but this way of embedded into 2 dimensions here, or I could use eigenvectors 2, 3, and 4 to go into 3 dimensions, should give you another idea about maybe a different way to do clustering on this. what else does the structure tell me?
Distance, right? The distance between the points?
Yeah, so now this distance makes sense. This actually, using the Euclidean distance between the points, seems like a reasonable thing to do. So often what people will do is they will embed it into 2 or 3 dimensions, and then they'll run some version of the k-means clustering problem after they've embedded it. So if they want, say if you want 5 clusters, it's not as obvious how to do it, and maybe this splitting into quadrants kind of is not the best way. So you could embed it into 2 or 3 or 4 dimensions. K-means clustering doesn't really, Lloyd's algorithm doesn't really care. And then you can run Lloyd's algorithm on top of this and find some clusters that way as well. So now, once I do this embedding, now I can use these as assignment-based algorithms, right? So this gives me a way of kind of taking the graph and putting it into a often low-dimensional, Euclidean space. Okay. Yeah, I've got some picture in the notes where I do the embedding based on where I use these eigenvalues as well. Okay, so this unnormalized Laplacian is kind of, it looks a little bit nicer. It has the property that each of these vectors is going to be a unit vector, and kind of it looks nice. It's easy. It's kind of easier when you draw pictures. It kind of makes more sense. But when you want to minimize the normalized cut, turns out you want to use the Laplacian matrix instead, which is defined slightly differently. So this is the normalized Laplacian, or often you call it just the Laplacian matrix. In the literature, you'll see various variants of how these are called, whether the Laplacian or normalized Laplacian. And so instead of using the degree matrix, it uses the degree matrix to the power -1/2. And so basically, if you have a matrix which is a diagonal, and you take it to some power, that's equivalent to taking each entry on the diagonal to that power. So I went from, so 3 to the -1/2 is going to be 0.577, for instance, right? And 2 to the -1/2 is 1 over square root 2 is 0.707. So that's where these entries came from. And so then the Laplacian matrix is written like this, or the normalized Laplacian is the identity minus d to -1/2 a times d to the -1/2. This is equivalent to also writing d to the -1/2 times the unnormalized Laplacian, so the d to the -1/2. You can also write it this way, and then the d, if you multiply the d -1/2, you can kind of remember this one was equal to d minus a. And so if you do this d to the -1/2 times d to the -1/2, that becomes the identity matrix. Right, so they're just like non-matrix algebra, that works out the same, and then you get this other term in the middle there. Right? So this is the regular Laplacian matrix, the normalized one, and you know the entries look similar to before, but they don't have quite the same nice, it doesn't the same property where the sum of these columns adds up to 0 for every column. You don't have that property anymore. What you did kind of do is you took, what this effectively does is it took this entry, which before was a -1, and it basically is dividing through by the square root of the degree of b times the degree of it's -1 divided by square root of the degree of b times the degree of d. All right, so I looked at the degree of the two vertices that it's corresponding to. So this has to do with this edge between B and C here. That's what I'm looking at. And B has degree 2, and D has a degree 3. So I'm normalizing by square root of the product of these. Turns out, so you kind of want to, it depends on both of the vertices. So I'm kind of normalizing them by the degree of both vertices is what is kind of going on here. And it turns out that if you want to minimize the normalized cut, then using this Laplacian, and then again taking the eigenvectors and eigenvalues, this one is more preserving the right properties of the norms. We're not going to kind of go through why that's the case, but so this normalized Laplacian corresponds to the normalized cut. And it's not that much more difficult to work with. You've just you've scaled each of these things with the adjacency matrix by the squares of their degrees. So it's still just as sparse as before and everything like that. Right? So now we want to take the eigenvectors of this matrix L instead of L0, and we're going to get this instead here. And it's going to look fairly similar. The first one you still want to ignore. This one you kind of say, ignore this one. And then the second one, right here, where this is lambda 2 and V2, is really what's telling you the best information on how to split them. Okay? And so if I draw a picture of this, and yeah, so in this case, I have scaled by 1 over lambda in each of the coordinates. So if you notice the ones here, the y-axis, which used V3, got divided by 0.72, so it's going to be, they're going to kind of be close to between -1 and 1, roughly in that range, but these are divided by 0.125, which is basically multiplying by 8. Right, but the maximum value I got was like 0.3438, so I got up here, this is like a -4 or something like that. -5, -4, somewhere in there. Okay, so now, if I look at this version, I can see that this the second eigenvector has really separated these 4 things from these 4. So now this is S. Right, so S, I flipped the signs. The signs really don't matter too much yet. Don't matter at all. I flipped the signs on them. That doesn't matter. But now I see much more separation here between S and S prime. So it's should be much more obvious how I want to cut this. And this did not do quite as much of pulling H away from everything else. It's kind of said, well, it's pretty far away from everything, but it has only one edge. So I don't want to really push that too far away. You really don't want to cut this one off because its volume, if I had it set just here, is not going to be as large. So the normalized cut score of cutting this is not going to be so big. So I'm not going to pull this one so far away from the data as I did with the unnormalized Laplacian. So if I look back at the unnormalized Laplacian, here, right? So H got pulled really far away from everything else. But I didn't really, that's not a great thing to cut. It doesn't tell me much to chop off H. And so when you have a lot more vertices, this is when you want to, this is going to work better. Right? So you're going to use this Laplacian matrix instead. Okay, so, yep.
Why is the distance from E to C so much longer than F to H? They both have just one edge.
Yeah, they both have one edge, but there's more to the cut going on, right? E is connected to G and H, which are not, these are not connected to anything on this set S before, right? Where C and D are connected, and C is connected to A and D, and these are connected to each other. There's a much stronger component going on here, and this somehow captures all those properties together. It's saying, really, these are really tightly bound. A, D, and B are all really close to each other because it's a clique. They're all connected to each other, and the only other thing they're connected to is C, which both A and D connect to. right? And C is pulled away because it's connected to E, but not so much. It's really concentrating, really putting in a similar geometric location things that are very well connected. It's the intuition I can give you. There may be a different mathematical way of giving intuition explaining that, but I mean, this seems like actually what you want. You really don't want to separate A, D, and B from each other in different clusters. They're as connected as they can be, right? So these are really close together. So if you did k-means clustering on top of this, these are really going to be one cluster. They're really tightly connected. Whereas, here this seems like a good cluster, but it's not as tightly connected, e.g. F and H. There's a clique there again, but what they connect to is different. This one connects to H, which is pulling the F one off in this direction, and E is connected to C, which is pulling that one off. So there's kind of not quite as tight a structure over here. Yep.
So we're gonna look into why this shakes out with it, or just kind of just use it?
Yeah, so we'll talk about the SVD and the eigenvectors a little bit later when we get to some parts that are in the regression part of class. And you'll get some more intuition there, but going beyond what I've told you in that these eigenvectors, the second eigenvector in particular, is the best way of drawing a straight line. It's kind of what I was, as much as I was planning to say in this lecture. Kind of diving into why it is requires much more machinery that we don't have yet. So in the PCA SVD lecture, we'll look more into kind of what's going on, and those are related matrix decomposition. Okay, so another important thing to mention is that I started with my input here being a graph. I said that my input was something like this graph here. And I have these vertices and edges. And this gave, gave rise to a matrix, right, where I have this adjacency and this degree matrix. Right, if I look at this adjacency matrix, these are values between 0 and 1. They're 0 or 1, right? But what else did we look at that had values between 0 and 1? So we talked about these, when we talked about similarities, right? So if I define a similarity, like the Jacquard similarity, between objects A and B, this is going to map to a value between 0 and 1. Right? So if instead of saying it had to be 0 or 1, I could say, well, let's map it to a value between 0 and 1, like the Jacquard similarity between these objects. If I do this, and then I can still create the adjacency matrices exactly defined that way, and the degree, or this degree matrix, I can just sum up the columns. I could sum up a column, and that becomes what the value is here on the diagonal here. I can use this instead. This is typically sometimes called, if I define it this way, it's an affinity matrix. Or if I use what's called, if I define the similarity as a kernel, then this guy becomes what was called the Gram matrix. So a kernel, what should I say about kernels? So a good way to think about kernels, so let's think the data points, if they lie in Euclidean space, I can define the Gaussian kernel. If these are vectors, then you can do something like e to the minus a minus b. More space here. Okay, so you can do something like e to the minus a minus b squared. And so this gives you a value between 0 and 1. This is a common kind of spatial kernel. There's a way you can do a polynomial kernel instead. And for certain classes of these kernels, this grand matrix tells you the similarities the same way, and you can use this instead of using this as a graph. And then you can use spectral clustering based on based on the similarity score. So how many people have taken the machine learning class? Did you guys do some techniques based on kernels? So you talked about some of these. So you can replace like a regular dot product with the kernel, and a lot of the techniques you use there go through. And so this is similar here, where I can replace an inner product with a similarity notion of a kernel, and then I can put this into a matrix, and I can do spectral clustering based on it. And this gives me a non-linear view of the data points. I only care about things which are, so for instance with the Gaussian kernel, if this is in one dimension, it looks kind of like this, where A is here, then the value of the kernel for value B is here. So it drops off after a certain value, it goes very close to 0. Or if it's close, it has a large value. And you can adjust this based on some bandwidth parameter, for instance. And that tells you how spread out this kernel is. Square this usually. And so this is a non-linear way of saying the things which are close to each other, I really want to make sure they're in the same cluster. Things that are further away, well, those I don't care so much about. They're far. They're not similar. So if it's far or it's twice as far, the similarity is still roughly 0. And so sometimes what people will do to make this faster is they'll do this and then they'll round down some of the entries to 0, and you can get a fairly sparse matrix. Okay, so using these notions of similarity or kernels, you can extend this spectral clustering to use these things directly. Okay. That was all I had planned to cover today. Any other questions about this spectral clustering or other clustering in general? There are types of clustering we didn't cover in class. Maybe you said, oh, why not? What happened to this type and how does that fit in? Okay, so the clustering homework will be posted online hopefully this afternoon or this evening. And then next Monday we'll start on the streaming part of class. We'll just spend a week on this, and then we'll do more stuff with regression. Inside the regression, we'll see some more streaming techniques. This is a way for doing kind of data mining where you keep getting more data all the time, and you want to maintain some sort of structure on the data. And so it's useful for very large scale things. And the sorts of things we'll be able to work with are going to be much simpler than before. We're not going to, there are ways to do clustering in this, but they're not quite as satisfying as things of just keeping simple statistics on the data. But the algorithms, again, will be very cute. Okay, great. So I'll post the clustering homework soon.